Okay, before I begin, who is taking the course on microscopy and nano analysis something? Okay. In second semester I have a series of lectures on surface methods. Also we'll be able to hear about STM, STS, all these techniques in more detail. So today it's going to be just an overview and a short introduction into STM. So if anybody is more interested in these techniques, you can call me or you can take the lectures in March, I guess. Okay, so this is the official beginning. Okay, so my name is Erik Zupanič. I come from Condensed Matter Physics department. Today I'm going to present the new scanning tunneling microscope that was just installed at the institute. The equipment is part of the Nano Center, Center of Excellence. So basically this instrument is available not for everybody, but anybody who has some problems, some ideas what to do with it. And today's lecture is to give you somehow an idea how this instrument works and what can be done with it. Okay, so we'll start with a more general introduction into scanning probe microscopy. So this is a definition I took from Wikipedia. It says that STM is a branch of microscopy that forms images of surfaces, so this is important, surfaces, using a physical probe that scans the specimen. So these are the typical techniques, scanning probe techniques. You should be aware of AFM, atomic force microscopy, maybe, let's say, scanning near-field optical microscopy, of course, STM, scanning tunneling microscopy. So what these methods have in common is that they use a sharp probe, either it's a tip or something else, and record the interaction between this probe and the sample surface. So it depends on what kind of interaction you're recording, you have then the different methods. A little bit about the history of STM. It was developed, not basically invented, but developed in IBM in Zurich in 1981. So these two guys shared the Nobel Prize for Physics for their invention. And this is basically the first prototype of STM. It was on permanent magnets in a lead ball, and this was cooled with liquid helium. So basically this was the first low temperature STM, but helium in that case they used it to levitate this whole STM head. I will talk a little bit about the problem of vibration insulation in these instruments. But okay, let's look at the STM. So what's the name? Scanning tunneling. So the STM operation is based on the quantum mechanical effect called the tunneling. So, okay, this should be better. So what is this effect? This means that a particle, in this case an electron, can overcome a potential barrier even if its energy is lower than that of a barrier. In this case, the barrier is the vacuum region between the STM tip and the sample surface. Let me just emphasize that this is basically the schematic representation. So these are the atoms of your sample, of your substrate, and this is the STM tip. And obviously the STM tip cannot be sharper than the atom. So this is just the schematic representation. Because it's very important that when you do STM, you use a very sharp STM tips. So what happens if you apply a voltage difference, a bias between the STM tip and the sample surface on the other side, and if you reduce the distance between the two. So the typical distance between the STM tip and the sample surface is a few angstroms. You will notice that the tunneling current will start to flow. And this tunneling current depends on the distance between the STM tip and the sample surface and the applied voltage. So these are the typical values that are used in the STM microscopy. So the voltage difference, the applied voltage between the tip and the sample is around 10 milli to 10 volts. The tunneling current is quite small, between a few picoamps and a few nanoamps. So you have to basically measure the tunneling current very precisely, and this is also one of the problems in STM. Okay, this will be maybe a little bit boring for some of you. Let's assume the simplest case, it's a one-dimensional case. On the right you have a tip. So this is density of states. This is the tip. This is the sample. They are separated by some small distance d. And these are the energy levels. So basically, we have an ideal tip. So the flat density of states up to the Fermi level. And all the states to the Fermi level are filled. Above Fermi level, we have empty states. And on the left, we have the sample. So this is the density of states of the sample. So what is density of the states? This is basically the information about the electronic structure of your material. This is the information you're really interested in. So what happens when you apply a voltage difference between the tip and the sample? So in this case, we applied a negative voltage on the tip side. We effectively raised the energy levels. And now what happens? The electrons, these electrons from the tip, can now tunnel into the empty states on the sample sides. So basically, these electrons go from the occupied to the unoccupied states in the sample. But the other question is, so what is the probability for tunneling? So the electron will tunnel through this empty region from the tip to the sample. The probability for tunneling is given by the square of the wave function of the electron in the tip. And the important part is this parameter d, so the distance between the two. So the tunneling probability, so the net tunneling current, is exponentially dependent on the distance between the two. This case, this is a constant which includes the work function of the tip and the sample, and of course this voltage difference between the sample and the tip. So let's try to evaluate this, this constant K. So work functions typically for metals around 4 or 5 electron volts, something like that. This is in the region of millivolts. And what we get is, 2K has a value of around 20 nanometers per minus 1. What does this tell us? That if we change the distance between the sample and the tip by 0.1 nanometer, so 1 angstrom, this will result in an order of magnitude difference in the tunneling probability. So a small change in the separation between the sample and the tip will induce large changes in the tunneling current. So if we approach the tip and the sample very close together, we will get some tunneling current. If we change this distance just a little bit, this will result in large changes in the tunneling current. So basically, the tunneling current is the measure for the distance between the tip and the sample. We can very precisely measure the distance between the two by measuring the tunneling current. We can introduce this concept of density of states, and this is a simplified form of the tunneling current, some constants. Then we have density of states of the tip around the Fermi level, density of states of the sample. Then we have some temperature-dependent Fermi-Dirac distribution of electrons. This is, of course, at 0 temperature. This is smeared a little bit at finite temperature. And then we have this term, which is called the tunneling matrix element. What does it describe? It basically describes the interaction of the wave function of the electrons in the tip with those in the sample. So why am I showing you this equation? Basically, the problem is how to evaluate this term. So this is the most simple case, one-dimensional case. Somehow, this is the value of these terms. But in a more realistic approach, it's basically impossible to evaluate this term, because it depends not only on the geometry, but also on the chemical structure of the STM tip. And now we're talking about the STM tip on the atomic level. So we are not talking if the tip is sharp or blunt or whatever. We're really talking on the few atoms on the end of the STM tip. And of course, you don't have any methods, any ways to determine what are the atoms on the end of the tip and how they are arranged. So basically, it's impossible to determine this matrix element. And this is basically the biggest problem in STM. Everything is very straightforward. Also, this equation it's very simple. But this term basically complicates the whole system. Okay. Next, I will present to you the basic three things that you can do with STM. STM imaging, STM spectroscopy, and the manipulation. So first of all, what is STM imaging? With STM, of course, you can image the surfaces. Of course, the surfaces have to be metallic or semiconductive, so you need the electrons to flow from the tip into the sample. So you can't observe isolated materials. If you want to do that, you should probably use, let's say, AFM, atomic force microscopy. Basically, we have two modes of STM imaging. This is constant height mode, this is constant current mode. So in both modes, we set the bias voltage and keep constant the voltage difference between the tip and the sample. In this case, the distance is kept constant, and we move the sample, we move the tip, line by line over the sample surface. What happens if when this tip moves to the right, the distance will increase, it will get shorter again, increase, and so on. This means higher tunneling current, this means lower tunneling current. And if you make a picture of the tunneling current versus the position of the STM tip, we can get a nice two-dimensional image of basically the topography of the sample surface. When is this mode used? Basically this mode is very fast, because all you have to do is move the sample or the tip over the sample surface. And this can be done very quickly. It's usually done by piezoceramic tubes. And usually this is also what you call a high-speed mode. Then you have another mode which is called constant current mode. So in this mode you always measure the tunneling current, and you keep this tunneling current constant by a feedback loop. This means when the STM tip is scanning over the sample surface, you always adjust the distance between your surface and the tip so that the tunneling current is constant. This is constant current mode. And what you record the vertical movement of your STM tip. Now you plot the two-dimensional image, you plot the changes in distance d, the vertical movement of the tip versus the sample position, and you again get a similar image, you get the topography of your sample. So this mode is of course slower, because when you scan over the sample you always have to adjust the tip. The tip goes up and down, up and down. So this mode is slower, but due to the exponential dependence on the tunneling current on the distance, of the tunneling current on the distance, this is the mode you basically always use when you want to image the sample surface. I will talk about this a little bit later, but this is then the movie, how this actually works. So again, this is the schematics. The tip cannot be sharper than an atom, but this is how it goes. So you're moving the tip line by line, and the tip goes up and down, and you record this vertical movement. This is how you image the sample surface. Another important point is the STM tips. So obviously, the sharper the STM tip, the better lateral resolution. The vertical resolution, so up, down, it basically depends on the stability of your host system. So it's not so dependent on the STM tip. But the lateral resolution depends on the sharpness of your tip. What tips do we use? We have a number of different materials that are used for STM tips. Usually we use tungsten, electrochemically etched. These are the scanning electron images of the tip. So this is 2 micrometers. So they are very sharp, but actually the tunneling current, so the whole process is done by the very end of the STM tip, so just on these few atoms on the end of the tip. And one of the biggest problems in STM is how to prepare these STM tips, because they have to be stable, they have to be sharp, and usually you want to keep them clean, so they should be metallic. But I won't talk about this now. If anybody's interested, I can explain you a little bit later. But what is so fascinating about STM and this related SPM techniques, for me, I don't know, maybe also for you. You have an STM tip. The dimensions, usually this is the microscopical object. This is something you can grab with your hand. So the tip is about 2 centimeters long. And on one side you have an STM tip, on the other side you have your substrate. So these are the atoms. This is the example for copper. So the distance between the atoms, let's say the diameter of the atoms is around 0.255 nanometers. So basically, with the microscopic object, with the STM tip, which you can grab in your hand, you can basically feel, you can touch the atoms of your substrate. This is the typical resolution. Usually, it's much better. what they usually show, if you take a magnifying glass and you magnify this by 150 million times, nowadays we know what a million is, what happens, these atoms will now become golf balls, but what will happen with your STM tip, if you magnify it by 150 million times, this STM tip will become 2,000 kilometers long. So this is somehow of an analog to give you an impression how precise you have to be when moving this STM tip. So basically it's like moving 2,000 kilometers long tip, and with the end of this tip you can touch individual golf balls. This is also the representation, so you see what is one of the biggest problems of STM. So it's the mechanical noise. So how to stabilize this tip, not how to really precisely move this tip. This is not a problem. You can do this nicely with piezo crystals. But how to stabilize the whole system, the whole instrument, that this distance will be constant. So we don't have the mechanical noise, this doesn't vibrate, this doesn't move. And this is basically what defines a good instrument. So how stable your tunneling conditions are. Sorry. Next thing, scanning tunneling spectroscopy. Well, it's nice to see the structure of your sample, of your surface, but even more important is to give to get some information about the structure, the electronic structure. If you want to investigate chemical, physical properties, you need something like information about the density of states. If you're working on molecules, you can do inelastic electron spectroscopy. This basically means you can measure the vibrational spectra of a single molecule. Basically, this is the fingerprint of a molecule. And with STM, for example, you can measure really the vibrational spectra of individual molecules. So not a bunch of molecules, but really individual molecules. Okay, these are different spectroscopy modes. These are not all the possibilities. These are just the basic ones which are usually used. I will just explain a little bit about the IV spectroscopy. So, how do we do it? If you again look at the expression for the tunneling current, what you would like to get is this term. So this is density of states of the sample. And basically you can very easily calculate this if you calculate the first derivative at some energy. Energy is the voltage difference, the bias. You get something which is proportional to the density of states of the tip and density of states of the sample. But since we said that, let's assume that the density of states of the tip is constant, basically what you measure is the density of states of the sample. So basically what you have to do, you have to position your STM tip over the place of interest, or molecule, atom, I don't know, some place on the surface. You have to change the voltage a little bit, you have to record the tunneling current and calculate the first derivative. Basically, this is how it's usually done. You sweep the voltage, you measure the current, you get something like this, calculate the first derivative, and this is directly proportional to local density of states. Why local? Because you're really making the local measurements. You're really measuring the electronic structure under the STM tip. So this is very important. And this is also one of the biggest advantages of STM. Not only you have high energy resolution, but you also have high spatial resolution. So you can measure the electronic structure, the properties of individual atoms on the atomic scale. So you can move the tip away from the atom and see how the properties evolve. It's a really nice instrument to study nanostructures, artificially built nanostructures. But this is, again, I will talk about this a little bit later. Usually what is the problem? If you do the numerical derivative, you will get a lot of noise. So basically when you want to measure some derivative, you use the lock-in amplifier. This is a classical scheme. So what you do, on your DC tunneling current, you superimpose a small AC modulating voltage. What you get a response in the tunneling current. And basically you feed this signal directly to the lock-in and you directly get the first derivative. So you don't have to do any numerical calculation, you directly get the signal. This is of course then a low noise signal. What is basically the derivative? It's basically the slope of this curve. What are the limitations? So of course you always have some limitations in terms of energy resolution. I will just show you an example. Let's say that this is your ideal sample. So this is density of states. So this is the energy. You have some delta function and some energy at 3 electron volts in this case. And what will happen from these ideal measurements? First of all, this delta function, it will broaden into a peak with a width of 2 times the modulating voltage. So the first limitation is this modulating voltage. So you should use as low modulating voltage as possible. But of course, you will get into some limitations, the noise, so this is limited. And then the second problem is this. This is the 3.2 kBT. This is the limitation due to the temperature. So we have some finite temperature. You're not working at 0 Kelvin. You're working at usually some low temperatures. And this is the full width at half maximum. So this is the temperature limitation of your system. This is basically the reason why you want to cool the STM, because you really improve the energy resolution. Just to give you an example, so at room temperature, your energy resolution is about 80 millielectron volts. If you go down to liquid helium temperatures, so basically this is the temperature that usually low temperature STMs are working at, you really improve the energy resolution to 1 millielectron volt. Okay, but again, if you go from 4.2 to 1 Kelvin, you will again improve this resolution by a factor of 4. So now you're into micro-Kelvin range. And this is why it's so important to lower the temperature even more, to 1 K. Now you have STMs which are working at 50 millikelvin. In that case, you again improve the energy resolution. This is why you want to drive the experiments at as low temperatures as possible. Okay, now the first thing you can do with STM, we said STM imaging, we said STM spectroscopy. The first thing is the single atom molecule manipulation. A nice thing about STM is that you can use the attractive, repulsive forces between the end of the STM tip and your absorbate. So you start with a flat, clean surface, you deposit some atoms, some molecules, whatever, and then you can manipulate them, you can move them. So this is so-called lateral manipulation, where you laterally displace the absorbate over the sample surface. What you do, this is the normal scanning distance, few atomic distances. So basically the STM tip will not influence the position of your absorbate. This of course depends on the absorbate, it depends on the temperature and so on and so on. Not so important at this one. If you reduce the distance between the two, then these forces will start to play a role, so they will become stronger. In this case, we moved the tip from the starting to final position, and this absorbate followed the path of the tip. So basically this is what is called lateral manipulation. You have different mode, pushing mode, pulling mode, sliding mode. It just depends on what kind of interaction you are using. In pulling mode you are using the attractive interactions, in pushing mode you are using the repulsive attractions. Basically you push the atom in front of the STM tip. This is something in between, so basically you catch the atom in the electric field. You can do vertical manipulation, you can pick up an atom on the STM tip, move the tip to the final position, and deposit your atom on the new position. So why is this so interesting? Because this is really the way to build nanostructures. So I mean nanostructures of individual atoms, not nanostructure on nanometer scale. This is something different. Here you can really play with individual atoms. Of course, you can play with different atoms. You can use magnetic atoms, you can use antiferromagnetic atoms, you can use combination of both. You can do this with molecules. I won't talk today about the manipulation you can do with molecules. You can break chemical bonds, you can form chemical bonds, you can change conformation of molecules. And all of these things you can do with individual molecules. So this is what you call single molecule chemistry. And these are the only instruments that basically allows you to do such kind of playing around. So this is just an example. Usually what people do when they know how to do the single atom manipulation, they do the institute logo. So ours is very simple, so no problem. So basically what you do, you make the image of your sample surface. You see these are individual atoms. So these are copper atoms on copper 111 surface. What you do, you manipulate, you move this atom from beginning to this end, from the starting to final position, and then you take the image again. Now we move this atom from beginning to end, now these two, and so on and so on. and in the end you get something like this. Okay, this is useless, but this is just to demonstrate how to do really the manipulation. Of course, you can have some fun. This is the world's smallest smiley. You cannot make it smaller. Yeah, probably you can use a few atoms less, but still. Okay, so just to summarize, I will show you some examples very quickly of the images you can get with the STM. So first of all, what kind of samples do we use? If you want to use the substrate just as a substrate for your experiments, then you use something that is easy to clean, with usually noble metal surfaces. This is an example of a copper 1-on-1 surface. So these are monatomic steps. You see that they are very clean. Again, what means clean in STM? This means that this surface, these are just copper atoms. You don't have anything else. This is why you do everything in ultra-high vacuum. If you take the image at higher magnification, you see the position of individual atoms. So this is the model, and this is then the actual image. You see you have some subsurface defects which somehow deform your surface of your material. This is the size of your image. So maybe some technical details, I will explain them a little bit later. But usually the larger scan size is about 1 micrometer. This is basically the limitation. This is an example of different defects on a copper 1-on-1 surface. You see that the apparent high is different, but these defects are always accompanied by this standing electron wave. So this is a nice representation that sometimes the electrons behave not like particles but like waves. So basically on copper 1-on-1 surface you have surface state electrons, and if you have a defect, what happens? This incident wave will scatter, and when the incident and the reflected wave interfere, you get standing electron waves. They are sometimes also called Friedel oscillations. Okay, imaging. Second thing, manipulation. You do whatever you want. Quantum chorus. First chemical reaction. It's basically an Ullmann reaction where you have a benzene ring and an iodine, you form a new molecule. But what is important is to know that you can manipulate atoms, molecules. Spectroscopy, really high resolution, limited by the temperature. And this is just a very simple combination of both. So imaging, manipulation, spectroscopy. These are chains made of individual copper atoms. So this is 1 copper atom, these are 2, 3, 4, 5, sorry, 7. So this is a chain made of 7 copper atoms. And now you can get some spectroscopy data out of this. You see some peaks. This is so-called quantum confinement, but I won't go into details. But this is basically ultimately what a physicist wants to do with STM. Wants to image, manipulate, do spectroscopy. And of course, all 3 things can be done with the same instrument in the same position. Okay, so now a little bit more technical details about the microscopy. So the first question is why you want to go to low temperatures. You have some obvious reasons, some of them are not so obvious. So the first is the theoretical, mechanical temperature stability. So your instrument really has to be stable. You're working on the atomic scale. To do this at room temperature, usually your instrument is not stable enough. You always have some temperature gradients in your STM head, and this causes so-called thermal drifting. So your images drift around. So you avoid this by doing your experiments at really low temperatures. Of course, you lower the electrical noise if you work at really low temperatures. Another thing, low temperature stabilize surfaces and surface absorbates. If you want to do manipulation, you cannot do it at room temperature. At room temperature, everything will move. They will just diffuse around the surface and you won't be able to do anything. So basically, you have to cool the surface to stabilize these absorbates, atoms, molecules. Usually, you have to go to temperatures below around 15, 20 Kelvin, something like that. As I said before, it depends on what you're doing, what kind of surfaces you have, what kind of molecules, atoms. This one is very obvious. If you want to observe some low temperature effects, you have to cool your sample. For example, if you want to work on superconductors, you have to go below the transition to superconductivity. and this, we talked about this, improved energy resolution in spectroscopy measurements. So you want to go to as low temperatures as possible to really get the most out of the instrument. You have many different STMs. You have ambient, ultra-high vacuum STMs. So if you want to work in ultra-high vacuum because you want to work on clean samples. If you want the samples to keep clean, you have to do everything in ultra-high vacuum. You have to clean the samples in UHV, you have to work in UHV. Then you have high temperature, room temperature, low temperature STMs. You have high temperature STMs, which is really funny. But if you want to observe some chemical reactions which only happen at high temperatures, or some catalytic processes or something like that, usually use high temperature STMs. You can observe how thin layers grow, and usually do that at high temperatures, and so on and so on. Then you have high-speed STMs, which are able to image the sample surface at a few hundred hertz. So basically, in our case, to take one image, it takes about 2-3 minutes, something like that, at least. These high-speed STMs, they can do a couple of hundred images per second. They are lower in resolution, and you have a lot of limitations, but sometimes you want to use these instruments. You can use magnetic fields, and so on and so on. So it's endless. It really depends what you want to do with your instrument. If you're more interested in some reactions, some catalytic effects, if you want to work with manipulation, if you want to just observe the surface structure, it really depends what you want to do. Okay, so why is this STM so special? It's because it works on this so-called Joule-Thomson effect. So basically everybody knows this effect. This is the effect that your refrigerator is working on. This is the basics. The temperature of your gas or your liquid will change when it adiabatically expands. This means you have a gas at some starting temperature. If you expand this gas, you will lower the temperature. This is how the refrigerator is working. This is how the liquefiers are working. And this is basically how our microscope is working. We have a helium gas bottle. We cool this helium gas to about 4 Kelvin, and then we use a very strong pump to expand this gas, and we get something which is cooled to around 1 Kelvin. So in this way, we can work not only at 4 or 5 Kelvin, which is typical for helium bath cryostats, but we can work at 1 Kelvin. Again, just the temperature difference of 3 Kelvin, it's not much, but this means the resolution, we improve the resolution by a factor of 5. These are again some technical details. If anybody is interested, I can explain it a little bit different. This is basically the main part of the instrument. This is the cryostat, the Joule-Thomson cryostat. So the upper part is basically very standard. So you have a vessel which is filled with liquid helium, and then around you have a vessel which is filled with liquid nitrogen. You have some radiation sheets, and here on the bottom you have this so-called Joule-Thomson stage. So this is the photo of this stage. So this is basically the STM head. This is where all the experiments are made. These are some connections. This is some tubes which are used for this adiabatic expansion of the gas. So this is the sample, this is the STM tip, and this tip then scans over the sample surface. Okay, again, I won't go into the technical details, just some data. So the typical temperature, if you operate with helium-4, so this is normal helium, the working temperature is around 1 Kelvin. This cryostat can also operate with helium-3, which is kind of really expensive and hard to get. You can lower the temperature to about 500 millikelvin. Of course, you can set the temperature. You have a small heater on the STM head, so you can vary the temperature. In this way, you can observe some phase transitions and similar. This is an important parameter. It's basically the measuring times. As you've seen before, so basically you use liquid helium, about 10 liters of liquid helium, and this helium will be good for about 6 days. After 6 days, you have to refill your cryostat. And this means you have to break your experiment, you have to retract the tip, you have to increase, you lose your position on the sample, you refill the cryostat, and then you can work again. And in our case, this is quite good, so basically you can work for 6 days. Typical microscopes, in the beginning, they were operatable for about 12 hours, so every 12 hours you have to refill. Then 1 day, now we're now 6 days. Okay, specifications. As I said, this is the maximum scan size. It's quite low. About the samples, basically the larger samples you can use are about 10 to 10 millimeters. But in our case, since we're interested in this manipulation studies, this is enough. Okay. Maybe some other technical details. This is again stuff which is maybe not so important, but you should be aware of. When you prepare a clean sample surface, you're not only interested in clean surfaces, you're interested in some atoms, molecule deposited on these surfaces. If you deposit something at your sample at room temperature, you will grow islands. So these atoms that you deposit on the surface, they will agglomerate, they will form islands. So this is how an MBA is working, molecular beam epitaxy. So you deposit something and you get some layers. But if you deposit in situ, this means when the sample is cooled to close to liquid helium temperature, you will get individual atoms, you will get individual molecules, they will not agglomerate, so they will be individually there. In that case, you can study them, you can move them, and so on. This instrument has 4 ports for in situ evaporation, so you can use 4 evaporators at once, so you can deposit 4 different kinds of atoms at once. And you have 2 additional ports if you want to use laser-assisted testing. Again, I won't talk about that. But sometimes you want to induce some changes with laser light. So basically you can shine with the laser light on your sample, and at the same time you can do STM measurements, which is a really nice feature. Okay, so this is how then the actual instrument looks like. It has 2 main chambers, so these are ultra-high vacuum chambers. This is the preparation chamber. We prepare the sample, we clean the sample, then we transfer the sample into the measuring chamber. This is the cryostat, here is the liquid helium, liquid nitrogen, and the actual STM head is in the middle of this measuring chamber. These are some dampers. This is the manipulator, which helps to move the samples in the ultra-high vacuum. About the equipment, annealing stage, ion gun. Ion gun is used for cleaning the sample surface. We have evaporation source, and we have this LIT-Auger spectrometer. LIT means low energy electron diffraction. IAS means Auger electron spectroscopy. So these are 2 surface sensitive techniques. One is to determine the crystal structure of your surface, and the other one is to determine the chemical composition of your surface. Sometimes this is helpful. Okay, this instrument you can, after this talk, you can come with me, you can have a look at this instrument, so you will see how it looks. About the control system, it's basically a very user-friendly system which allows you to do all the things you want to do, from manipulation to spectroscopy. It's partially open software, so basically you can also define your own experiments, write your own VIs, so basically it's a lab view-based software. Okay, maybe at this point, this is basically the first low temperature STM here at the Institute, first in the Center of Excellence. So we have another low temperature STM. This one is it's older one, it's homemade. This is basically how the STM head looks like. This is then the second system, which is now in the testing phase, to be so-called NMR STM. This is basically, it will be used to detect RF signals. So again, I won't go into details, but it's important to know that we have some experience in low temperature STMs. Okay, so somehow to summarize this talk, this is a message take home. STM is a powerful nanotechnological tool, and you should remember somehow that you can do 3 things. We said imaging, manipulation, spectroscopy measurements. Of course, advantages, very versatile method, you can do a lot of different stuff with it. You have high spatial, high energy resolution, you can perform local measurements. Of course, every method has its drawbacks. The biggest drawback is the tip shape and chemistry, which influences your measurements and are usually not known, so this is the biggest problem. Sometimes complicated interpretation of the results, which is basically common for all methods. And in general, it's a difficult technique to perform. It's very time consuming. So basically, preparing the sample, preparing the STM tip, and then you can do your actual experiment. It takes a lot of time. Okay, so I'm ready for your questions.
How flat should the surface be so that we can operate?
Basically, depends on what you want to do. But if you have a really corrugated surface, I'm not sure what you're gonna see. So, but the Z movement is about 0.1 micrometers, so 100 nanometers. So in that range should be. Okay, anybody interested in seeing the instrument? Yes or no?
Yes.
Okay. Okay, thank you. So it's basically just across the street. It will take 5 minutes.